GraphsFloydWarshall is a dynamic programming algorithm that is going to give you the shortest distance from every vertex to every other vertex. Whereas we can use general graph search algorithm to give us, for example, we can use Dijkstra's using general graph search algorithm to get shortest distance from A to every other vertex. But Floyd-Warshall is going to give us shortest distance from every vertex to every other vertex. So how it's going to work is there's actually, conceptually, we can ask the question, given vertex I and given vertex j, we can ask the question, is there some vertex k where if this is weight 0, then weight 1, weight 2. Can we find such a k such that W0 is greater than W1 plus W2? So if we can find an edge, an intermediate edge that even though we take more steps, it has a shorter path, or shorter path between I and j, then we want to reset that inside our adjacency matrix. So Floyd-Warshall is going to iterate over 3 variables. Variable k, which is the intermediate node or vertex, I and j, which are our two vertexes that we're testing. Okay. So initially they're going to start out at 0 and they're going to iterate up through every vertex. Okay. So for sake of brevity, to make you can see that it's going to start at 0. And this is going to be a boring one because they're all equal to 0. So, going from A to A is not shorter than going to A and to A. Since these are all pathways of 0, that's not interesting. So if we look at a case, let's say we look at a case where, let's say k is equal to 1. I is equal to 0, and j is equal to 3. So if you can read this up here, it's going to be a 2D array, and we're looking at what's the relationship between A at ij. So A at I0, j is 3. This relationship, forgot I changed my graph. 3. So what's the relationship between A and ij? So ij is going to be 3. Okay. So 3 is going to have some relationship to, now we can go from A at ik, which k is equal to 1. So we have this 1 here, plus A at kj. So A at k. So k is 1 and j is 4, or 3, sorry. So we have a 1 here as well. So we look at this relationship, we can see that 3 is greater than 2. And if we look at the graph, you can see that this number is representing the edge from A to D. So this edge here. This number is representing from I to k. So I is A, to k is 1. So A to B. And then this number represents k, which is 1, to j, which is 3. So you can see that taking the direct path has cost 3, or taking a path through B actually shortens the distance between A to D. So when this is the case, where this is our current edge inside our matrix, and this is the shortened weight according to Floyd-Warshall, now I can update I can update this edge to cost 2, because that's what we just discovered. And you don't have to worry about it being symmetrical, because you're iterating through everything, so you'll actually cover the other case when the variables are swapped. So you'll cover the case where I is 3 and j is 0. So that will fix itself. You don't have to worry about that. But that's how FloydWarshall is going to work. You run the algorithm once, and you will have the shortest distance be from any vertex to any other vertex. If you run it again and in the graph or the vertex or the matrix changes, then that means there's a negative cycle. So there's something. Let's say this is not 1. Let's say this is negative 800. So you're saying that instead of staying at A, so from A to A should have cost 0. But if this edge is here, you're saying to travel 1 here, travel down here, I've traveled negative 799, 3 over, so negative 796. You're saying that it's actually faster to travel through these vertices than to just not move at all and stay put. So negative cycles will break FloydWarshall, but negative edges will not. Yeah. So that's just a general concept of FloydWarshall.